have here, can I get distracted a little bit, is that we have one more method called Simpsons Rule. And I think I'm going to stop for the next few moments because every time I start, I think someone's going to turn up. So let's just give a few moments, get that done. Right, Gabby, can you hear me? And Esther, can you hear me?
I can hear you.
Oh, good. Right. Well, I'm glad that you turned up. I mean, you don't need to, but it's great that you can. So, plus, you can give me feedback. So if there's things that don't make sense, I bet you there's more people in the class that they also won't make sense for. So you'll be helping those people too. So a quick recap again, what we've done. We're going to introduce one more rule called Simpsons Rule, and these questions will appear in section 7.7, the second topic section of homework for this week, week 1. I haven't gone into any details about what this formula is, but we will. And essentially, Simpsons Rule, as long as you have an even number of intervals, is very accurate. In fact, it's more accurate than any of the other, for the same number of strips, any of the other techniques we've got. So for instance, I could do a right 6 or a left 6, right? So 6 strips, and I could find what L6 is, what R6 is. Nothing wrong with that. But it's pretty inaccurate, unless you're really lucky and the shape's not too weird. Of course, once you know left and right, you can get trapezium 6, which is essentially the average of those two guys, which is quite good. Trapezium 6 will always be better, typically, than those two. We then looked at midpoint 6, and midpoint 6 is even more accurate. But there's one more guy. Simpsons 6, I guess I'll do it over here. Simpsons 6. Simpsons 6 is what this formula allows us to calculate. So you might think, well, what do they do different? Because everybody else is some kind of rectangle. That's the biggest difference. Simpsons Rule is not each strip is a rectangle and you add them all up. Each strip, let's take a random strip, might look something like this. And you got your curve doing your curve thing, right? Now, if we were doing left, we would go this guy. If we were doing right, we would go that guy. If we were doing midpoint, we'd do a rectangle in the middle. The trapezium is just the average of left and right. They're all covered. So what is left? You might be thinking there's nothing else you can do with a strip. But this guy, Simpson, was really clever. He discovered a new way to find the area of the strip. And he took those 2 points and he found a quadratic curve, a little piece of a quadratic, joining the start to the finish. And he found a way to calculate the area of a strip where the bottom is straight, the sides are vertical, and there's a quadratic curve at the top. Now, although that curve there isn't necessarily quadratic, you would agree that a curve is probably going to be the best fit, because at any point, you're going to have a different quadratic for that bit, another quadratic for that bit. So each quadratic is a different quadratic. And he found a way to do that, which is amazing that he did, and we're glad that he have. And when he did this, he then calculated the formula using n strips, and the formula ends up being this guy up here. So I guess the question is, well, what are all these funny F1s and F2s, and why is there 4 of these and 2 of them? It's part of what it is. The formula does this. What we have is F0, F1, 4 of them, 2 of this guy, 4 of this, 4, 2, 4, 2, and you finish with 2, 4, 1. And that's the pattern. So it's one of those situations where I think it's easier to see it in application than to take this, because this is essentially the generalized formula. So I'm going to take a function. I'm going to call it x cubed plus 2x. Right? And we are going to find the area under the curve from 1 to 3. And we are going to do 8 strips, which is quite a lot. And we're going to do Simpsons Rule. So we are basically going to find Simpsons 8. Once I get the answer, I'll put it in here. Well, you begin very much the same way that you do with all the other techniques, like left 6 and right 6, or left 8 and right 8. You find delta x. In this case, delta x is b take away a over n, 3 take away 1 over 8, 0.25. You then create your table. And you're going to have your starting value, which is 1, and then 1.25, and then 1.5, and 1.75, and oops, and 2, and 2.25, 2.5, 2.75, and last but not least, 3. Now, for each value of x, we will then calculate what this function is equal to, what its y-coordinate is. So nothing I've done right now is really any different from how you would approach a left 6 or a right 6 or a left 8 or a right 8. So what I'm going to do now is calculate all these guys, but using a table of values because it's quicker. Bear with me for a few moments while I load up TI-84 emulator. Okay, looking good. Ooh, that's not good. Excuse me a minute. I got this huge, ridiculous screen that I don't want, so I'll just do it this way. Right, and I'm now going to go in and are you seeing a calculator emulator? Can anybody see that?
Yes.
Okay, so because I have had in the past, I spent 10 minutes talking about things on a calculator, and then at the end, someone says, "We can't see that." And then after I swear a couple of times, I go and I do it again, right? So here we go. I go y equals, the function was x cubed plus 2x. I then go to table setup. There we go here. And the start value was 1. And delta table is really the same thing as our delta x, which is 0.25. And that's that set up. Make sure those two say auto. And then I'm going to go second table. And there we are. So you bear with me for a few moments. I'm going to do a little bit of cheat here, but this is really only for speed. It's not going to do much. Typically, when you do these questions, you have to do them to 4, 5, or 6 decimal places. And I certainly could do that, but I don't want to, only because it slows things down. But if I needed 5 or 6 decimal places, do you notice how I can just scroll over there and get them? I'm going to pretend that this answer is we're only going to use our data to 2 decimal places. So the next one is 4.45. After that, it's 6.38. The next number is 8.86. At 2, the answer is 12. At 2.25, it's 15.89. And 3 more guys will be done. 2.5 is 20.63. The last 2 numbers are 2.75, which is 26.30 if you round it up. And the last one is 33. So hopefully that you're used to and able to do that. Okay. Right, that you know how to make your calculator and do a table of values to speed things up. So there's that table of values I've got. Now over here, you can see the formula for Simpsons Rule. Let's tell you what these F0s and F1s are. This number, the value of the function, right at the start is called F0. This guy is F1. This guy is F2. This guy is F3. This one's 4, and so on. So if I'm doing 8 strips, do you notice that there's always going to be 9 numbers in my table? And you notice that you count them with that guy is called F0 and the last one is F8. So if you do a table and you finish on an F7, but you know there's 8 strips, then you've some wrongs, not right. You've forgotten one of the terms in the middle. Maybe you went 1.52 by mistake, whatever it is. There's something missing and you should fix it before you continue. Now, although there are 9 numbers there, you still only get 8 strips because you think about it, you've got the start value and the finish, and then you've got the ones in between. If you wrote all those numbers down, can you trust me, you would have 8 strips. Is it a little bit clearer now what all these F1s and F2s are? They just represent the value of the function here. F1 is this guy. In this case, F8 is the last guy. So I want to do Simpsons 8. It's going to be delta x divided by 3. And now I got to apply all of these. Now, some people who are much braver than me just go straight into the calculator and they go something like 0.25 divided by 3 times a bracket. And they go, one of these plus 4 of them, plus 2 of them, plus 4 of them, plus 2, plus 4, plus 2, plus 4 of them, plus 1 of them, close the brackets and hit enter. And every time virtually I do that, I screw it up. There are just too many things being multiplied and added that I get out of sync. I multiply something by 4 when I should have done a 2 or vice versa. So I slow the process down. It's one of these guys, 4 of these guys, 2 of these guys, 4 of these guys. These are called weighting. So that has a weighting of 4. This is a weighting of 2. This is a weighting of 4. This is a weighting of 2. This is a weighting of 4. And finally, this is a weighting of 1. You see how the pattern of the weighting works with the table. It goes 1, 4, 2, 4, 2, 4, 2, 4, 2, and you finish with the 4, 1. Now, according to the formula, it's one of these guys, 3, plus 4 of, 4 of that guy. So if you bear with me, I'll just do it on my calculator, my emulator one. So 4 times 4.45. 4 times 4.45. And the answer I get is 17.8. 2 of that guy, that's 12.76. 4 of this guy, again, I'll not risk that one. I'll go 4 times 8.86. I get 35.44. Oh, and while I'm doing it, done you, done you, done you, done you. 2 times 12 gets me, 2 times 12 gets me 24. Done you. 4 times that guy, see what that is. 4 times 15.89. That gets me 63.56. This guy is going to be 41.26. This guy here is going to be 26.3 times 4. So there we go. 4 times 26.3. 105.2. I guess I'll do it down here. and then 1 times 33. Now, this is much longer than just sticking it in the calculator and going for glory. But if I screw up and one of these numbers isn't correct, maybe I multiplied by 2 instead of 4, whatever it might be, I now have the individual pieces. Maybe the mistake is when I was adding them up, I forgot one, right? Whatever it might be. Because I've got these, I can check them again to make sure I multiplied them right. And then I can just be more careful when I add them. And if I do that, I should be fine. So our calculation is now going to be 0.25, which is delta x, divided by 3, times whatever all of that adds up to. So that's what calculators are for. Actually, I should be able to try that without a calculator. That's risky, but I'm going to do it. 6, 10, so maybe not. I've changed my mind. 3 times 3 plus 17.8. Then I can add 12.76. And I can add 35.44. Keep going, add 24. 63.56. 41.26. 105.2. And 33. And that comes to 336.02. And now I can do that over that times that. So I'll do that now. 0.25 times 336.02. And then divide by 3. And the answer I have here is 28.00, let's say 17. So that is Simpsons rule in a nutshell. You take your start and finish value and how many strips you need, and you find delta x. You then start at the beginning, in this case 1, and do all the numbers, right, add delta x all the way, and you get this entire table from your calculator, your TI-84. And then you factor in one of these, a weighting of 4, a 2, 4, 2, 4 to the end. Each of these guys gives you these fellas here. Let me do a head count. 1, 2, 3, 4, 5, 6, 7, 8, 9. Good. If there's 9 numbers, I haven't missed any. So you add them all up, times that, divide by 3, and you get 28.0017. And now I'm going to try and convince you that even although that's only 8 strips, this estimate for the area under the curve is extraordinarily accurate. So, any of you want to take a bet here? Would you be impressed if this was good to 1 decimal place? Would that be impressive for you? What do you think, S? 1 decimal place. Would that impress you? Gabby, would it impress you then? There's no correct answer to that question, you know that. I'm not sure if we have communication issue, but we'll just keep going. So, let's see what it is equal to. Well, you might say, well, how can I check? Right now, all I have is a numerical technique. I don't want to do the whole thing again just to check that I get the same 28.0017. And how accurate will that be? Well, there is a way that you can check this on your calculator. So you bear with me. I'm now going to show you how to do a numerical check on the area under this curve from 1 to 3 and see what we get. And hopefully everything comes out good. And here it goes. So you go y equals, you got your curve. You go to your window and you go from x equals 1 to x equals 3. And then you do a zoom 0. And what that will do is just draw the piece of the curve from 1 to 3 that you're trying to find the area under. It's pretty boring, right? It's just a simple curve, but that's fine. What you now do is you go second calc. And the option you want is number 7, which looks a little bit strange, but I'll talk about that after we've finished. That is the formula for finding the integral that we would call the area under the curve of a function. So you choose that option number 7, you press enter. And it says lower limit, which in our case is 1. And then you say upper limit, which is 3. And I'm about to hit enter here, but before I do that, the TI-84 calculator, I have no evidence to this, but I'm very, very sure that this is what happened, is that it has internal to it a program, which is essentially Simpsons Rule. And instead of doing Simpsons Rule to 8, it probably does it to like 80,000, right? Some extreme number, which we know is really accurate. So let's hit enter. And it does a little animation, I guess. And the answer is 28. You should be impressed. The correct answer for the area under this curve is 28. Look how good it is. And remember, that was 8 strips. I mean, it wasn't like 80,000 strips, right? It was just 8. What is it? It's about, oh, going 1, 2. It's about 0.04% out. I think most people would be really happy with that kind of accuracy. So Simpsons Rule is typically going to be the go-to method if you had a question like, what is the area under this curve? Estimate the answer, as accurately as you can using 5, 8, 10, well, it won't be 5 for Simpsons, 6, 8, 10 strips kind of thing. Now, the good news is that now that I've shown you that one question, every single question that gets you to do Simpsons Rule is essentially replace that function by whatever the question is, have a different start and finish value depending on the question, and have a different number of strips. But the process will stay the same. You'll find delta x, you'll create the table, you'll do the weighting of them, you'll do delta x over 3, which is this piece. You will find the individual pieces, these guys here, add them up, then do the calculation. Bingo. You got your guy. Any questions?
I am still confused on the times 1, times 4, times 2.
Right. So where did that 1, 4, and 2 come from? Is that what you're thinking?
I get that you get it from the formula,
Right.
but my question is, how would you go about it if there were not, let's say, like more than 8?
Oh, so suppose there was a different number, like, right, the only thing that you have to have is an even number, right? So 1, 2, 3, 4, 5, 6, 7, 8. There's 10 strips. There's 10 numbers. Oops. There's 11 numbers, so that makes it 10 strips. Right. This guy is F0. F1, F2, F3, F4, F5, F6, F7, 8, F9, F10. And your question is, well, how did the 1-4 pattern work? What's like this? One of these, always start with 1. Then you have 4. Then you have 2. Then you have 4. And then you have 2. And basically you keep going until you get to the end. Now at the end you have to be a little bit careful, but let's see what happens. Oh, I'm almost finished. Finish with 1.
So it's always start with 1 and finish with 1.
Yep. And all the
Okay.
guys in between are just 4s and 2s, alternating between the 2.
Oh, okay.
Does that help?
Okay. Yeah.
Right. So you could have 4, well, I wouldn't do Simpsons Rule with 4 strips because it's probably not worth it. Because even, Simpsons Rule's not going to be great with 4 strips, right? So, but after 4, let's say 6, 8, 10 strips, Simpsons Rule is phenomenally good, right? So that would be, if somebody just said to me, I want you to find the area under this curve, pick any method you like, but you can only use 8 strips. I'm doing Simpsons Rule every time. Because for the same number of strips, Simpsons Rule will knock out the park any of the other ones as far as accuracy goes. It's that good on that. Any other questions?
Nope, I'm good.
You're good. Right. So what I'll do for a few moments is good, both of you are good. I like to see that. Is I'm now going to go and show you. Let me check out this one because I've got answers and they're very yeah, they're very distracting. So I'll kill that guy off. It'll take me a few seconds to load up what I need. And then we'll show you what the homework questions look like and maybe talk through a few, or if you want me to do another Simpsons role thing, for sure I can do that. Right now I'm just loading it up and see what we've got here. That's good. And use a student, almost there. And there we are. Go. And go. Now, move that over here. And I need screen back. I've lost my screen. Where's my screen? Oh, stop sharing. There we are. I've got my screen back. Okay, so right now you should be looking at the same screen that I had a minute ago. Is that correct? Yes? Thumbs up. That works too.
What are we looking for?
You should be looking at the white screen with the tables written on it. Is that what you can see right now?
Yes.
Okay, so now I'm going to jump over and look at the homework questions. And the first thing you're going to notice is, what the heck is this thing? Here. Let's make that bigger. I'm not sure what kind of screens you're using. There. Can you see that nice and clear? Right? That guy there.
Yes.
This is the notation that we use to represent, right now, the area under the curve. So the function is 3 times the cosine of x squared. You're going to do it from 0 to 1. And maybe you're going to use the trapezoid rule or the midpoint rule, whatever it might be. And can you see here it's 4 strips? So that's basically what we did at the beginning of the week, right? Now, it asks you to use the trapezoid rule. So that means find T4. But if you remember what we did last time, the way you get T4 is you find left 4 and right 4, and then you add them together and half it. So even if it doesn't tell you to find left 4 and right 4, you really do have to find them. Great. And midpoint 4. And then it says that one of these is an underestimate and one of them is an overestimate. So you simply just put that guy into the calculator, and you should be able to tell. If a function is going downhill, right, it's decreasing all the time, then won't one of those, in that situation, won't the trapezoid and the midpoint, one of them will be big and the other will be smaller than each other. Well, the small one is an overestimate and the big one's, the small one is an underestimate and the big one is an overestimate. So let's pretend I know the answer. Let's suppose that one of them said the answer is 12. That's the underestimate because that was a small answer. And the other one said 23. And that would be a very inaccurate answer, but at least you know that the guaranteed, the real answer is between 12 and 23. In this question, the function is going to be the sine of the square root of x. You're going to do it from 6 to 9, and you're going to do it with 6 strips. You're going to do T6, M6, and now Simpsons 6. Are you clear in your head what you're being asked to do here? What the function is, what the start and finish is, and the number of strips? We comfortable, we know what's going on there. Somebody put it in chat. I am good. Okay, I'll take it. That's what you were talking about. Same idea. A new function. 8 strips from 0 to 4. This doesn't need to be x's, although most of the time it is. Equivalent to that in mathematics would be the square root of x cosine of x dx. It would get you the same numerical value. Trapezoid, midpoint, Simpson. There's your function. There's your number of strips. Trapezoid, midpoint, Simpson. And we'll talk about that one later. And we'll talk about this one. So for the first 4 questions, do you want to see another, let's say, Simpsons rule or midpoint rule or trapezoid rule for any of those examples? What is the one that you'd like to see? Can't see any comments. I guess lack of responses also means everything's cool, right? Are we good? You know that there's a little guy over here where you can go like that. And if you click on that, it saves you having to type things and I can see it. Esther, we'll pick on you. Do you want to pick one of those little guys? You'll find it in reactions and do a thumbs up for me just to show me you know what it is. Yay, Gary did one. Esther, can you do one? Oh, Esther's having issues. Oh, there.
Where am I looking at?
Okay. When you look at the bottom of Zoom, there's a whole list of things, but the one that you're going to look for is the one that has a little happy face and a plus next to it, and it's called reactions. It's towards the right-hand side. Right, click on that one and pick a thumbs up. Now, suppose you don't like what I've done. Go to that one now and pick a thumbs down. Yeah. And if I tell a funny joke, which I'm about to, you can cry your eyes out laughing because it was so funny, right? So that might be an easier way for you to communicate, both of you, right? Oh, you're all joining in now. Okay, so let's tell you the joke then. It's a very quick one. What, or not what, how many psychiatrists does it take to change a light bulb? At this point, you would probably say, I don't know. And the answer is only one psychiatrist, but the light bulb has to want to change. You can now do an icon with you crying your eyes out because it's that funny. Oh, okay. We're good. Right. So I did ask, do you want to see Simpsons Rule one more time? Does anybody give me a thumbs up if you want it one more time, or a thumbs down if you don't really need to? You're pretty sure you know what's going on. I'll go either way. Yeah, we're good. Right. Perfect. Okay. One of there's not a lot of benefit to these ones, but one of the benefits is, see, once you've done one, haven't you done all of them? I mean, the process doesn't change, just the numbers and the function you use might. So we are now going to move on to a special question here, which I'm trying to, yeah, okay. Here is a puzzle that they've got, and it looks something like this. Imagine you wanted to find, right, the area of that kidney-shaped pool. And it's 5 meters between the start of the pool, which would be probably over here, all the way to the end of the pool. So if I don't know why you might want to find the area, but actually, if you know the area and the pool is 2 meters deep from left to right, then won't the volume of water be the area times 2? So you might use it, in fact, to find out how much water do I need to fill up that swimming pool. Or if you wanted to get, in some places they cover the pool, especially in the winter, and you want to know, well, I wonder how many square meters of material I need to buy to cover that pool if I wanted a very, precise shape. Okay. And we're being asked to do Simpsons Rule, and Simpsons Rule is going to be n equals 8. Now, I'm not going to go through all of Simpsons Rule, but I will set up the table, because once you've got the table, the rest is pretty straightforward. The guy that they call 8, so I want you to imagine that there's a missing line going along here, right? The x-axis. That guy there would represent 0, right? A is the beginning. And it's being measured in 5-meter intervals. So let's see. 5, 10, 15, 20, 25, 30, 35, 40. So that would be, wow, they're rich. I mean, they've got half a football field almost of a swimming pool. Right, that's Hollywood swimming pools. Right? Now, what would delta x be? Right. Well, I actually already know what delta x is, but wouldn't it be 40 take away 0 divided by 8 as a calculation? And that ends up being 5. But they already kind of told me that, didn't they? So that was kind of not necessary. Now, these guys I do not like. I think it would have been much better if they'd said find f of 0, f of 1, f of 2, because technically those are the numbers that you should be using in your table. But this basically is what the x side of your column is going to look like. So your x's are going to start at 0, and then you're going to go 5, 10, 15, 20, 25, 30, 35. Oh, shooting space. Did you notice I never swore there? Because I'm really good at not swearing. Evidently, enter doesn't work. You have to click out the box and do 5. Then click out the box and do 10. And then I'm getting bored doing this. Can you imagine I finished it? Wouldn't the last one be 40? Okay. So I'm now going to leave that, and we're going to find out what essentially the value of the function is. And the value of the function are these widths here. So I'm going to go back in and close this off. And I'm going to construct my table. So our table already know that delta x is 5. We have x, and we have the value of the function f of x. There's your 5. Oops, there's your 0. Almost forgot 0. There's your 5. There's your 10. There's your 15. There's your 20. There's your 25. There's your 30. There's your 35. And finally, there's your 40. And these guys came from that kidney shape. So you know the kidney shape looks something like that. At this one, which corresponds to 0, there is no width. Then the next one, which would be the guy that's here for 5, it happens to be 6.2. And then the next one happens to be 7.2, 6.8, 5.6, 5, 4.8, another 4.8, and I'm left with one last guy. That guy over there is at the position 40. What is the width of the swimming pool there? That's 0. What's that guy? Any takers? Too shy to tell me? Yeah, 0, 2. You know that. There we go. So technically, don't I just need to know that in this table and we're pretty much ready to go. So let's do the pattern. 1 of them, 4 of them, 2 of them, 4 of them, 2 of them, 4 of them, 2 of them, 4 of them. Oh, I'm about to run out, finish with 1. And so Simpsons 8 will be delta x over 3 times all these things multiplied and added together. And then delta x would be what, 5/3. I'm pretending I know the answer. I don't. It's 1,000, say. Then wouldn't our answer be whatever, 5,000/3, if that's what we have? Are we comfortable with that guy? Okay. Someone take some in. See? And my feedback, yes. Oh, good. You did the thumbs up one. Thanks. That makes my life so much easier. Right. So you'd finish it off and you do what you need to do. And that is Simpsons Rule. And I can make a prediction here on that story. If you were trying to measure that, and it's, imagine you were trying to measure something that's irregular, like a kitten-shaped swimming pool, or, you know, some of them are really ornate and weird looking. And it'd be very difficult because there is no formulas for shapes that look like that. I mean, in fact, there's very few formulas, right? We get rectangles, triangles, bits of circle, we get ellipses, but in general, we don't have formulas for irregular shapes that just have curves to them. So this is really the only practical way. But what's cool about it is Simpsons Rule would get that answer correct to, 3 or 4 decimal places, would be my guess, which is very accurate for a limited amount of usage. In fact, in a lot of cases, when you do real experiment, your answers are observations. Like, I observed the object and its velocity was here, and then 10 seconds later, its velocity, and 30 seconds later, at this velocity, and like 40 seconds later, it stopped moving. And if you wanted to find the area under such a curve, which is time velocity, what you're calculating is how much in total that object moved, what its total distance is. And the only way you could do it is through a table of values, because that's the only numbers information that you've got to work with. Now, what happens, as it does, if they give you a table, and yet I apologize beforehand here, because you aren't going to like this question, but there's only one of them. Here is a table of values. It's the power consumption, P, is how much power was being used in a country, starting at 6 a.m., which is midnight. From midnight, I say, to 6 a.m. So that is midnight. That's 1 p.m., 1 a.m. in the morning, there's 3 a.m., and there's 6 a.m. And here are the power consumption values. And you are being asked to use Simpsons Rule, round off your answer, thankfully, to 1 decimal place, but that's still not going to make your workload that much less. And if you look at this table, I think they've saved space by sticking them together, but technically, if you wrote it, wouldn't it be one very tall, right? Very tall table, right? So you imagine this bit being bolted onto the bottom. Now, using Simpsons Rule. Cool. But how many strips? Well, 1, 2, 3, 4, 5, 6, 7. Keep going. 8, 9, 10, 11, 12, 13. Doesn't that mean then 13 numbers is 12 strips? You know, if you've got 7 numbers in your table, that's 6 strips. And the reason for that is you've got a start and a finish, right? So you don't count both of those. So in this question here, what number is delta x? Well, to get delta x, you have to look at these guys. I guess I should call it delta t because the variable's called t here. Would you agree it's 30 minutes? Right? Now, that doesn't mean delta x is 30. And the reason why it's not 30 is because down here, you see the units are hours. So it's half an hour. So delta x is 0.5. So there's a little place you may have went wrong. So delta x over 3 becomes 0.5 over 3. And then you do 1 of these guys, 4 of these guys, 2 of these guys, 4 of these guys, keep going. Finally, 4 of these guys and 1 of those guys. And you are pretty much done. So I'm going to pretend that I did all that. So can you imagine you did 1 of these and 4 of them and you had all the guys and you added them up and you get, I don't know, 17,000, whatever it really is, to finish with 0.5 times that divided by 3, and I'm going to pretend I know the answer, which again I don't, but it's 1507.2. So if that was the case, then you could say that the total megawatt hours, I'm going to put a bigger number there, was 9,500 megawatt hours over the entire period. So can you imagine that you're in a power station and you know, it's a gas power station, whatever it may be, it's nuclear, and you have a meter that's basically registering every half hour and how much power is being sucked away to the villages and the towns that are it's supplying energy to. You'd end up with a table like this. But if somebody went and said to you, how much did we generate today? What's the total amount of megawatt hours that we produced? And the answer would be the area under this curve. It would be this guy here. I'm pretty sure that in places like power stations, they have lots of digital dials. One of those digital dials would be like a running total. How many megawatt hours has been used so far today, starting at midnight? How are we doing, guys? You got a thumbs up for that one, I hope. If not, ask a question. I'll be pleased to help. Well, that's Simpsons Rule finished. You know how to do trapezium. You know how to do midpoint. You know how to do Simpsons Rule. Each one does the same job. It basically estimates the area under a curve. So we have just a couple of little things now to tidy up. And I'm now going to have to return to some stuff that I missed from the first section. So give me a few moments. Section 5.1 now. Kick over and I'll show you the things that we're still to cover. Basically, we're going to do a thing called Riemann sums. Now, last time we dealt with things like that. Left 6, right 6, covered that, no problems. Left 6, right 6, upper and lower, find a left 6, find a right 6. This is the new guy in town. If you look at this table, and while you're kind of looking at it, I'm going to be copying it down, at least what I need to copy down here. And it's actually a snapshot of a rocket taking off. And at launch, that's time 0, its velocity was 0. So obviously it's still on the ground before they hit the thing. 10 seconds later, it's now have a velocity of 185. 15 seconds, it's now climbed to 319. 20 seconds, it's now at 442. At the 32-second mark, which is what makes this a little bit different from the typical table, it's now climbed to 742. And then 59 seconds, which is an unusual number as well, it's climbed to 1,315. It is really moving. At 62 seconds, which is actually not that far late, it's only about 3 seconds later, it's up to 14. And then by 125 seconds, which is just over 2 minutes, it's now 4,131 feet per second. So I've taken that table and I've just copied it down here. And we're being asked to find the distance traveled. The distance traveled is basically, I draw a pretend picture of this from 0 to 125. Is the area, there's 125 there, is the area under a velocity time. So if you've ever done physics, you probably know that, right? The area under a velocity time curve is its distance traveled. So let's see what we have here. This is not Simpsons Rule. They never mention Simpsons Rule. In fact, I don't know if they mention anything, but except Riemann sums with 6 intervals. That's not much help, because technically all of them are Riemann sums of some sort. So I'm going to do this guy, and I have a choice. And I don't want to do wind back. 1, 2, 3, 4, 5, 6, 7, 8. Would you agree there's 8 numbers here? 1, 2, 3, 4, 5, 6, 7, 8. So actually isn't Simpsons Rule a non-starter? Because you need 8 or 10 or 12 strips. Simpsons Rule only works, the pattern only works with an even number of strips. I'm kicking out midpoint. And the reason I'm kicking out midpoint is that I only know 0 and 10. I don't know what the middle is, which would be 5. That's my argument for that. So I'm going to do a left or a right, and you might think, oh, that's great, until you look at the table again. Do you notice that the spacing is not equal? That's a spacing of 10. That's a 5. That's another 5. That's a 12, right? They're different. So we have to adapt the formula that we've been dealing with, right? Let's say left 7, right? 1, 2, 3. Yeah. Let's suppose I wanted to do left 7. Typically, in a normal situation, wouldn't it be delta x or a whole load of guys added up? But that works only because each of the strips is the same width. In other words, delta x is the same number. Now we have to figure out a way of dealing with this fellow. So, can I cover this? I can go. There is the first 2 numbers, right? From 0 to 10, that rectangle is 10 units wide. And it could be 0 or 185. Now, 1, 0, the other is 185. Since I'm doing the left-hand side, won't I do 10 times 0? Now, let's look at the second strip. The second strip starts at 10 and finishes at 15, so that makes it 5 wide. What number do I use for the height? I use the left one, the 2, so that's 185. Right, if we move down, the next strip, 5 units wide, choose 319. The next strip is 12 wide and 442. The next strip is this one, so that's what, 27. times 742. The next strip is from here to here, which is what, 3. And the height is, we're going to use is the left-hand side one, which is 1315. And then the last one, it's 63 wide. And the height I'm going to use is 1430. Are you comfortable about how I had to adapt the L7 rule to cope with the fact that each strip, virtually each strip, had a different width? So sometimes delta x is 10, but sometimes it's 3, and sometimes it's 5 or 12. Does the logic of what I did there make sense to you? Right, good. So I am not going to do that, and I'm going to just pretend that the answer is 2,400 because I want an answer, right? But I want as accurate as an answer as I can. So I'm now going to do R7. Now, the only real difference with R7 is, right, so there's your first strip again, so it's 10. But when you do the right-hand side, don't you pick the second one, 185. And then the next strip would be 5 units wide. And wouldn't the height be this number, 319? And then the next strip is 5 again. And the one that you'd pick is 442. And can I just so dot, 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 right? And you finish off with the last strip, which would be these two. And the last strip would be 63 times 4,131. And I would do that calculation, and I'm going to pretend that the answer is 3,000. Well, because of the shape of this, won't that be an underestimate and not an overestimate? So I know that the real distance traveled is somewhere between 3,000 and 2,400, right? And I don't really know which one of these is better. They're equally good or equally bad. But I'm not finished yet. Can't I now find one last estimate? Trapezium 7. So here's your question. How do I find the value of trapezium 7 using these two guys? Anybody? How do you do that? How do you do it? What's the formula for calculating trapezium value? Last chance. L7, R7, and half it. Right? So in this case, if these numbers were correct, it'd be that number plus that one over 2. So that would get me, what would that get me? 5,400 over 2, 2,700. So that would be the best answer I could get using that table of values. You got any thumbs up for that one or thumbs down? Do you want me to explain something? Okay. You know you are allowed to put thumbs down. It does tell me, I said earlier, if you're having an issue, someone else is going to have an issue and you're helping everyone, including yourself. So let's return now to the bits and pieces that we have not covered. We've now covered question 4. 5 is pretty much the midpoint rule. And now we have these guys. And these are Riemann sums. After the German, his last name is Riemann, I can't remember. Johann Riemann, I think it was. Riemann sums. So let me show you what's going on for a Riemann sum. It's the beginning. We haven't, and the next section we're going to do this, but it's the beginning of how we are going to set up a method for not estimating the area under a curve, but getting the exact value of the area under the curve. So we are going to use notation called sigma notation, because it's a very useful way of writing down things that involve adding a whole load of things together, right? Now, if I went and said to you, what would R7 look like if I had to just calculate it? And the function that we're dealing with, we're just going to call it f of x, right? And we're going to start at x equals a, right? And we're going to finish at x equals b. How would you set up the working, right? For calculating, say, R7. So in this case, n would be 7. Well, the first thing I'd do is I'd find delta x, which in this case would be b minus a over 7. And that's all I can do. Until you tell me what numbers b and a is, that is going to stay put as a b minus a over 7. Now, if I set up my table, I start at a. Now, who would the next number be? It would be a plus this guy, right? And then it would be a plus 2 of these guys. So this one would be a plus 1. And let's just call it 1 delta x, one of these guys. And then it'd be a plus 2 delta x's. Then it would be a plus 3 delta x's. And then down here it would be 4 delta x's, 5 delta x's, almost done. 6 delta x's, and you'd finish, and you've got 7 delta x's. And that guy would actually be equal to b. You can check it, but it is. Now, this fella is going to be called f of a. This guy would be f of a plus a delta x. This one would be a plus 2 delta x's, and so on. And this last one would be the value of the function a plus 7 delta x's. And now I can do right 7. Right 7 is delta x times this guy plus this guy plus that one, all the way to the last one, which is that. Now, if I had thought better, I would have started here and wrote the thing as one big line. But can you imagine that that is a little bit messy and not very concise? It's hard to tell, you know, all the moving parts are just so many of them. So this is what it looks like, the sigma notation. Sigma I equals 1 to n means that you're going to be adding up 7 things. And when I do the right-hand ones, do you notice that I missed the first one, but I do everybody else? So it will be delta x times the value of the function. Well, when I is, what's that one there? When I is 1, yeah, you get that guy. When I is 2, you get that guy. So if I do a plus delta x times I, that represents all of these guys being added up. All I've done, pull out the delta x, and this represents the first strip when I is 1, put in 2, put in I is 3, put in I is 4. And what that does is it basically takes this and condenses it into that. And we call these things Riemann sums. And pretty much exclusively when you do Riemann sums, you're always doing a right. There'll be a right 2, a right 10, a right 1,000,000. So suppose I do Rn. Well, delta x is b take away a over n. Okay, I can handle that. Each one of these guys here, right, that's essentially called x0, that's called x1, that's called x2, and this guy down here is going to be called x7. xi, which would be any one of these, like x of any position you like, would be a plus I delta x's. And so we're going to do I equals 1. Oh, by the way, that there has to be 7 because it's 7 strips, but now it's going to be n. It's going to be delta x f of a plus delta x times I. And all we need to know is that delta x is this thing, right? And these guys, you know, that represents each one of these x coordinates down here. So how on earth is that going to help us? Well, suppose I find Rn using this sigma notation, right? If I did 10 strips, it would be I equals 1 to 10, and that would be R10. If I did a million strips, R a million would be I equals 1 to a million. You see, the only thing you need to change is essentially that number there, right? It's whatever n is. And here's the cool part. The area under a curve, that's the exact value, is the limit as n tends to infinity of Rn. So let's see what the logic is. If you do a million strips, you get a really good answer. If you do a billion strips, you get an even better answer. But if you theoretically could do an infinite number of strips, wouldn't the area then be the exact value rather than just a really good estimate? And that's the trick. So the area under a curve, the exact value, is the limit as the number of strips tends to infinity of the Riemann sum. And the Riemann sum is written down in sigma notation, like this guy. Okay, let's look at question 7. The function f of x in this story is 6 plus sine squared x. X is going to go from 0 to pi. We are going to find our Riemann sum, Rn. So let's see what we have. Delta x is b take away a, pi take away 0, divided by n, which ends up being pi n. The exact value of our area, then, is going to be the limit as n tends to infinity of what you get if you add all of these guys up, delta x times the value of the function at a plus delta x times I. Now, I have some details on this question that I didn't have before. Delta x is pi over 2 times a is 0. Delta x is pi over n times I. So I now am going to find the limit as n tends to infinity. Pi upon 2 times the value of the function at that point. Now, I know the function is 6 plus sine squared x, so I can take it just a little bit further. And the function is 6 plus sine squared of x, so it's going to be 6 plus sine squared of that guy. And that is us finished. Let me show you what that looks like. A lot of people find these a little bit weird, and I understand that. Now, part of the puzzle's already been filled in for you. You see they've done this bit and this bit. So the bit that I kind of did goes something like this. I hope it takes pi as a word. Pi. No. A bit pi. Good. So it's pi, brackets, 6 plus sine squared. Good increase. Oh. Can you do sine squared in WebAssigned, or do I have to do sine of the whole thing being squared? Does anybody remember doing WebAssigned, how that worked? I've forgotten. Anybody can help me here? Otherwise, I'm just going to go with the second method because I know that. Okay. Then I'm going to go, to get sine squared, I'm going to do a bracket around it. I'm going to do the sine of pi I divided by n. Does that guy? Looks like I'm going to have more brackets than I need. That guy. So actually, I can take out one of these brackets. Web assigning gives you more than you need.
You're on the wrong box.
I'm in the wrong. Wow.
You should be in 7.
Well caught. Gotcha. Okay, so that guy there should be pi over 2. So I forgot that as well. So let's fix that. Yeah. Then there's 6 plus this guy squared. I think I can put the square here. That looks good. Okay, so that's essentially what I did. Let's check it out, see if there's a better version of that. Okay, where is my mistake? Oh, okay. 6 plus sine squared, that should be good. Pi I over n. Probably doesn't like the square I squared it. Let's check. Pi over 2 is good. That's good. Okay. I'm going to try something a little different now. You can bear with me for a few minutes. I'm pretty sure it's just the way I've written the answer, not the answer itself that's causing the issues. Let's do a view. And go back and we'll look at the answers. Of course, they've changed it a little bit. And I said pi over 2, and now I realise that my mistake was pi over n, which I actually wrote pi over n, but then just didn't write it down. So let me go back and show you what I did write. Yeah, pi over n. But for some reason between here and there, it turned into a 2. Right, so that guy should have worked, right? If I typed it in with an n instead of a 2, we would be correct. Right, that one's going to be a head scratcher. You'll probably want to watch some other videos, other people describing it, because I think it's one of those things that we need to find a way that makes most sense to you. But we still have a few more to go. So here is question 8. And question 8 is actually, is it 8? Yeah, question 8, we'll come back to the other one up there in a minute, is they've already given you the Riemann sum. And somehow or other, you have got to figure out what was the function and what was the interval. Now, unfortunately, you've got the answer in front of you. That's a little key. Let's see if we can figure out where the function comes from. Doesn't this 3 over n, typically that's the value of delta x? And isn't this guy here the f of x? So I would look at this and say it's the square root of a number 1, which is always 1, plus a guy. The guy is going to be x. So this would be 1 plus x. That's that guy. And then you might say, well, how do I know it's 0 to 3? Because it might be minus 3 to 3 and so on. And that's a little bit trickier, but what I do is, if you go here, right, and you plug in your values, 1, 2, 3, 4, 5, 6, 7, and so on, whatever you need to do, since delta x is this fella, and that is also delta x, it tells me that you start with a 0, because 1 plus 0 would get you that guy, and that's why we choose that one. And now we've got this guy, and I'm going to try this one again. This is a different one, but I want to see if we can do it. F of x is x squared e to the x. X goes from 0 to 3, and there's going to be n strips. Now you can see the answer there, but let's try and show you where the answer came from. Delta x is b take away a over n. 3 take away 0 over n. So there's my delta x. Here's my Riemann sum. It's going to be the limit as n tends to infinity. Sigma I equals 1 to n. Delta x, the value of the function at a plus delta x times I. Delta x is 3 over n. A is 0, so this becomes 0 plus 3 over ni, so it just becomes 3 over ni. The function is this guy, so think of this as the x that you get that goes in here, and you are going to get 3 over n I squared e to the power of 3 over n I. And what I'm doing here is just some tidying off. You get 3 over n. If you take this guy and square it, you get 9, you get an I squared, and you get over n squared. And then to finish, combine the terms. 9 times 3 gets you 27, I squared over n cubed, e to 3n over I. Now, Weber sign actually would have accepted that, which is correct. All I did is make it look a little prettier. And that's pretty much everything covered. I guess the question to finish with is, are there any questions? Okay. No, okay. Right, I do realize that this last piece with the Riemann sums is really quite weird and not something that you've spent any real time in, and you probably should, as I say, look up some videos on Riemann sums and just get a little bit more comfortable with what we're doing. Right now, there are only 3 questions, and we've kind of went over all 3, so there's a good chance that you'll be able to figure out what the answer is based on what I've got here. In the big scheme of things, it's how we prove the technique for finding exact area under a curve. But in reality, you're going to find that this is not what you do like for lots and lots of questions. What we eventually do is we say, look, here's some very specific examples, like the area under a quadratic, maybe the area under a straight line, and the area under a cubic typically. Right, there's the three standard ones. And we will show you how we start with a function like, x squared plus 1, and work through this process and get an answer, a numerical answer. And that numerical answer represents the exact value for the area under a curve. And that's for next week. So